Okay. So, hello everyone. Hope the midterm went okay. I apologize for not being able to do the interactive lectures as I had planned today. I've been having terrible issues with my internet access, and it's also why this video is later than I would have hoped in posting. But anyways, yeah, I'll try to go through in as much detail as I can exactly how I would have approached this exam if I didn't know I had written it and I were attempting to solve it as best I could. Okay, so we can just go through the various questions in order. I'll see, roughly try to spend an equal amount of time on each question. Okay, so we can have a look at the first problem. So it asks us about splitting this group of 20 people into a red team, a blue team, and a yellow team. And then it tells us that the red team must have 5 people, and the blue team must have 8 people, and the yellow team must have 7 people. And then 2 of the people don't like each other and must be on different teams. So we need to figure out how many ways there are to form the 3 teams. So if I were looking at this question, I would think to myself, well, this is the first question on the exam, and it's pretty transparently a counting problem, which makes sense because counting was the very first thing we did in the course. So I'm like, okay, I'm supposed to count something. So what am I supposed to count? I'm supposed to count the number of ways to form various teams. And the structure of the question kind of suggests that the way you should approach it is to figure out, first of all, how many teams could be formed without this restriction of the 2 people who don't like each other, and then try to compensate for that restriction afterwards by subtracting. So this is kind of a general pattern for counting problems that ask you how many ways are there to do something with a specific subset of the ways excluded. So here we're asking about the number of ways to form the teams, and we're excluding a particular collection of teams. So I'm going to think I'm supposed to count something, and then I'm supposed to subtract off some things to compensate for the teams which are excluded from the question. Okay, so first thing I want to count is the total number of things without the hypothesized exclusions of certain subsets. So we can just say, if we're not taking into account this group of 2 people who really don't like each other, we can say that we're just splitting 20 people into groups of 5, 8, and 7. And so this is what the multinomial coefficient 20 choose 5, 8, 7 is designed to count. Okay, so now we need to go further and to compensate for how many splittings are ruled out by the existence of this pair who don't like each other. So in the solution here, I have the phrase hat distribution. That's a hangover from a previous version of this question. You can think of it as a typo. Instead of hat distributions, it should say, we consider how many teams are ruled out by the existence of the pair who dislike each other. So we're going to call the two people who dislike each other X and Y. And then we're going to count the number of splittings which are ruled out by their bad relationship by figuring out how many teams are there where they're both red, how many teams where they're both blue, and how many teams where they're both yellow. And then we're going to exclude these things. So first of all, let's think about the situation where they're both on the red team. So if they're both on the red team, then there's 5 spots on the red team. So there's 3 left to be filled by the people other than X and Y. So there's 18 people other than X and Y, and we're doing a task which is equivalent to splitting them into the 3 remaining spots on the red team, and then the 8 on the blue team and the 7 on the yellow team. So this is exactly what's supposed to be counted by the multinomial coefficient 18 choose 387. And then you can do exactly the same thing for the 2 other subsets which need to be excluded, specifically the subsets where they're both on the blue team and they're both on the yellow team. So if they're both on the blue team, then there's 6 other spots on the blue team and 18 other people to be divided into 5 red, 6 blue, and 7 yellow. And then if they're both on the yellow team, then there's 18 choose 5, 8, 5 ways to split them up. So in conclusion, we get a final answer of 20 choose 5, 8, 7 minus the 3 other counts we figured out we needed to exclude. So we subtracted these 3 other multinomial coefficients, and a computer told me this is 68,787,576. So that is what it is. Okay, so now let's have a look at this problem too. So if you were in the interactive lectures last Wednesday, which were based on preparing for the midterm, I warned you that this type of problem would be on the exam, where you're asked to verify an extremely simple statement using nothing but elementary logic and the axioms of probability. So this type of problem is obviously kind of difficult and unnatural for the human brain because it's asking you to think very much like a computer. It's asking you to give yourself absolutely no charity in high-level concepts or thought processes. It's asking you to manipulate axioms and symbols according to formal rules and derive a certain result. So this kind of computerized thinking where we're just manipulating symbols according to formal rules is ultimately what underlies the entire structure of theoretical mathematics. And, you know, the reason I'm trying to force you to think in this computerized way on this problem is just to demonstrate to you that this kind of thinking is possible and it's impossible to be wrong if you do it correctly. It's like if you're manipulating symbols according to formal rules and axioms and you follow the rules and axioms, then whatever you do is going to be a logical consequence of the axioms. That's a tautology, but that tautology is all of theoretical math. So what I'm asking you to do with this problem is just to dip into this kind of formal symbolic manipulation to give yourself a sense that the axioms of probability plus elementary logic really do imply literally everything we're doing in this course with symbolic manipulation, even though it's obviously impossible for the human brain to think on such a symbolic level with formal rules beyond the very basic, simple kinds of statements you're asked to prove in this problem and the analogous one on the practice exam. So, this problem is supposed to ask you to prove something which hopefully should be intuitively obvious, and it's asking you to prove it with absolutely no human brain allowed. It's asking you to prove it with symbolic computation. Okay, so how do you find your way through the maze of symbols to derive what you're asked to derive from the axioms of probability? Well, what I would first do in looking at this question is to kind of see to myself that whichever nasty person wrote it is kind of trying to trick me a little bit with this double implication thing. It's like the question tells me about three events, A, B, and C, and it says that A implies B and B implies C, so therefore we're supposed to prove A is no more probable than C. And this A implies B and B implies C, it's like, okay, I know that those two things are just making it more awkward for me to say that A implies C. Because, whoever wrote this question could have written it saying, just give me events A and C, assume that A implies C, show PA less equal PC. But the writer of the question did not do that. They obfuscated things by putting in this intermediate event B. So I'm going to be hostile to this obfuscation and attempt to remove it by doing exactly what I would like to be doing, which is proving that if one event implies another, then the first one is no more probable than the second one. So that's what I'm going to do. And when you're doing something in a mathematical proof and it's not immediately solving the question you're asked, it's often useful to separate it out as some kind of intermediate proposition, or what mathematicians often call lemmas. So I have this intermediate proposition, proposition 1 you can see here, which is doing so this proposition 1 is solving the question I would like to be solving. I'm thinking, whoever wrote this question is trying to confuse me by throwing in this intermediate event B, and I'm going to clarify things by solving the question exactly as I would if it didn't have this extra confusion thrown in. So I'm just going to say, all right, give me events D and E such that D implies E. Then I'm going to prove that probability of D is less than or equal to probability of E. Okay, so now I say by elementary logic, a bunch of symbols happen. And the rule with elementary logic is that there's a thing called a truth table. You may have learned about this if you've taken a course in computer science or discrete mathematics. A A truth table is a computational method for verifying elementary logical statements. If you're not familiar with truth tables, you can draw Venn diagrams to help yourself determine which sequences of symbols are valid in this context. And so if I draw a Venn diagram of E, I can see that E splits up into D and E or not D and E. So if E happens, then either it happens with D or it happens without D. Therefore, E is equal to D and E, disjoin not D and E. Okay, and then if D happens together with E, it's obviously impossible for not D to happen together with E. So we can say that D and E and not D and E is impossible. And okay, so I know I'm supposed to use the additivity axiom for mutually exclusive events, because the other two axioms of probability, the unit interval axiom and the axiom of certainty, are really pretty superficial, and you're never, ever, ever going to get anywhere useful by only using the first two axioms of probability. So in order to get anything off the ground with the axioms of probability, you need to somehow incorporate the additivity axiom for mutually exclusive events. So I've done some symbolic manipulations with elementary logic, and I can apply the additivity axiom for mutually exclusive events to arrive at what you can see as equation 1. So I'm going to say that the probability of E is equal to the probability of D and E plus the probability of not D and E. Okay, so now we can see another thing of elementary logic. We can say, all right, if D automatically implies E, then saying D happens together with E is exactly the same thing as just saying that D happens. It's like, if I know that when it's raining, the ground will be wet, I can say that if it's raining and the ground is wet, that's equivalent to just saying that it's raining. So I can rewrite this equation 1 by substituting the probability of D for the probability of D and E. And then I get this equation: probability of E is probability of D plus probability of not D and E. And then, okay, so the unit interval axiom tells me that probability of not D and E is non-negative, and so I can delete it from the equation and get an inequality, which says probability of E is greater than or equal to probability of D. And that's exactly what I was looking for. Okay, so now I've solved the question I would like to be solving without this intentional confusion on the part of the question writer introducing the intermediate to event B. But luckily, well, not luckily, because I was strategic in proving my proposition 1, I can now just kind of reap the benefits and solve the problem I'm asked to solve in a very straightforward way by just citing what I already proved. So I'm going to say, okay, I'm going to apply this proposition where I take D equal to A and E equal to B. And then the proposition tells me that probability of A is less than or equal to probability of B. And then I'm going to say by applying the same proposition with D equal B and E equal C, it tells me that probability of B is less than or equal to probability of C. And now I'm not even thinking about logic or events or probability at all. I just have three real numbers, PA less equal PB less equal PC. And I know that inequalities for numbers are transitive, so I can conclude PA less equal PC. Okay, so there are various other ways you can try to get around the question writer's obfuscation of the real issue by introducing the intermediate event B. But no matter how you get around that, you're ultimately going to have to do exactly what I did in proving Proposition 1 in order to address the main issue once you've got around the obfuscation with the intermediate event B. Okay. So let's have a look at the next question. Okay, so this question says, assume that 99% of people hiding in basements are annoyed by aliens, and 99% of people who are not hiding in basements are not annoyed by aliens. Also assume that 6% of all people are hiding in basements. What proportion of people annoyed by aliens are hiding in basements? So, we need to figure out how we're going to interpret the numerical data in the question. And so the first thing you always want to do is define some events. And the data in the question clearly refers to two events. It refers to the event that a person is annoyed by aliens and the event that a person is hiding in a basement. So we can translate the information given into the question into mathematical language based on those events. So it's going to tell us if you're hiding in a basement, then you have a 0.99 probability of being annoyed by aliens. And if you're not hiding in a basement, then you have an 0.99 probability of not being annoyed by aliens. And then I also know that the probability of hiding in a basement is 0.06. So as soon as I see data like this, I think to myself, this data is exactly set up to do reflection of conditional probability through Bayes' rule. And we can see that what we're asked to find in the question is exactly the reflected conditional probability of B given A. So, all right, we can catch that we have exactly the right data to reflect a conditional probability with Bayes' rule. And so let's do that. We have everything we need. We can say that the only minor changes we need to make before plugging everything into the formula is to just say that, okay, if not A given not B is 99%, then A given not B is 1%, and if B is 6%, then not B is 94%. So we can just plug all those numbers into the equation, and a computer told me this is about 0.863. So, I don't know. If I were annoyed by aliens, I guess I would want to be one of the roughly 13.7 who aren't hiding in a basement. But my odds of that aren't great. Anyways, I don't know, maybe if you are annoyed by aliens, hiding in a basement is a good thing. Maybe it's better than the alternative. But anyways, that's how we solve this question. Okay, so we can move on to the next question. So this question is pretty closely modeled on some problems we solved in the lecture, where we're doing a similar thing of considering infinite sequences of events and trying to construct the probabilities of infinite combinations through downward or upward continuity and turning infinite Boolean operators into limits. So, whenever you're dealing with a probability question that asks about forever or, eternity or infinity, at least if you're talking about events, you're going to need upward or downward continuity of probability somewhere, because you have an infinity in your events and you need to get that into an infinity in your numbers, and infinity in your numbers means you need a limit. So pretty much the only way to turn an infinite Boolean combination into a limit is upward or downward continuity. So just based on the fact that this question is asking about infinite sequences of events, I can clue into the fact that I should probably be thinking about upward and downward continuity. Okay, so way you always want to start the question is by defining an event. So let's define an as the event that the philosopher lives for n days. And so we're asked to verify that the complement of this event the complement of the infinite conjunction is certain. So the infinite conjunction of an means the philosopher lives forever, and the complement means the philosopher dies. And so we're asking to prove that the probability of eventual death is 1, or equivalently, the probability of infinitely prolonged life is 0. So we can see what we're supposed to do here is prove that the probability of this infinite conjunction is 0. Okay, so in order to get any kind of numbers out of this infinite conjunction, we definitely need to know the probability of the various events within it. And so how are we going to compute the probability of these events an? Well, so the question tells us that there's some constant c which is strictly less than 1, such that on the first day, the probability of living is c, and on each subsequent day, the probability of living given life on the previous day is exactly the same constant. So using the tower rule, we can say, all right, I have an initial probability of A1, and then I have a whole long list of conditional probabilities that follow on from each other in exactly the right way to apply the tower rule. So I know that the first probability of A1 is C, and I know that all of these subsequent conditional probabilities are also equal to C. And so what I can do is I can just say this expression is the nth power of C, because it has n terms and every single term is equal to C. Or I should say n factors. Terms usually refers to a sum. So there's n factors in the product, and so we can say it's equal to the nth power of C. All right, so now let's try to work continuity of probability into this problem, because we know we're going to need it because we need to take an infinity from inside the probability symbol to outside of the probability symbol. And what we can say is all right, so if the philosopher lives for n plus 1 days, then that automatically implies they lived for n days. So the next event in this sequence implies the previous one, and we can say that this gives us a decreasing sequence of events. So if you have a decreasing sequence of events, then the downward continuity of probability tells you that the probability of the infinite conjunction is equal to the limit of the probabilities of the individual events, which is, if you're familiar with the term infimum, this is a decreasing limit which coincides with the infimum of the probabilities of A. Infimum is a concept in real analysis which generalizes the idea of a minimum to infinite sequences. So it's like the probabilities of AN are getting less and less and less. If C was like 1/5, they would be like, it would be 1 over 5, and then 1 over 25, and then 1 over 125. So the probability of each AN gets less and less, and so the limit is more or less a generalized minimum, where the probabilities are decreasing and decreasing and decreasing, and the only number which is an appropriate bottom for this list is 0. Okay, so if you have any number which is between 0 and 1, then as n goes to infinity, its powers approach 0. So we can see that the probability of the infinite conjunction of the AN is 0, as we were asked to find. So I got some emails about this question asking whether the phrase perfectly in their favor means that C is less than 1 or C is less than or equal to 1/2. So I would advise to interpret the phrase perfect odds or perfectly in your favor as meaning the odds are 1. So I think perfect odds mean odds are 1, and what the question is supposed to suggest is that the odds are less than 1. However, I think it is somewhat reasonable to interpret it as saying that their odds are never in their favor, which would mean the odds are always less than or equal to 1/2. So if you didn't catch that the word perfect is supposed to mean less than 1, and you just interpret it as saying the odds are never in their favor, so they're always less than or equal to 1/2, then you can get full credit for that on this problem. I will say, though, that if the odds are 1/2, the philosopher would probably be pretty sick. The kind of philosophical message of the question is that no matter how close to 1 C is, you're still going to die. So even if you believe you're super, super healthy and you have a 99.9999999% chance of living every day, because you're not perfectly healthy and the chance is less than 1, you're still going to die. Okay. So, So this is a question that is kind of based more on modeling a large structure which you've already seen than trying to come up with something completely original. I I think this problem would be too difficult to put on an exam if I hadn't solved similar problems in the lecture. But, kind of the idea behind this problem is that it's supposed to teach you to replicate and adapt relatively complicated solutions that you've seen to some extent before, because that's also an important part of mathematical and scientific work, is not only just coming up with new things on your own from scratch, but learning how to take pieces of structure that are too big to come up from scratch and adapt them to your situation and figure out how you can kind of leverage whatever other person built this structure for your purposes. So, there's a certain model for calculating probabilities about infinite conjunctions or disjunctions of events, and that model usually works pretty close to how this question worked and how to the related questions in the lectures worked. Okay. So now we have this problem 5. So this problem 5 is just supposed to test whether you know what a probability mass function and a cumulative distribution function are. This is just kind of a high school definition recall thing where you're given some information and you're given some definitions, and you're just supposed to demonstrate that you know how to apply the definitions to the information. So it asks us to determine the probability mass function of X. So we can see that there's 4 possible values for X. We can lose 3, we can lose 2, we can gain 2, or we can gain 8. And so once we know the possible values of the random variable, in order to get the probability mass function, what we have to do is to compute the probability that the random variable hits each one of these particular values. And so we can compute the probability of a value by saying, okay, these things are, first of all, conditioned on flipping a fair coin. So I'm going to multiply all the probabilities by a half to take into account flipping the fair coin. And then I'm just going to do the uniform probability formula where I check the number of cubes with the color I'm interested in, dividing by the total number of cubes. So we have an example here. So we have the probability of X being -3. We can say, all right, so I'm going to take the 1/2 from flipping the fair coin, and then I'm going to take 2/7 because in the first urn, there's 2 blue cubes out of a total of 7. So that way I get 1/7 as the probability of X being -3. Okay, and so then we can do the rest of the calculations in exactly the same way and fill out the table you have on the screen here. So when you see these kinds of questions that are just asking you to show that you remember a definition, for these things, the explanation requirements are pretty low. I've written a bit of explanation in the solutions here, but in terms of grading the problems for this sort of definition recall, you can get a perfect score just by doing what you're asked with no additional explanation, because there really is no explanation needed other than to implement the precise definition of the words. So we can have this table for the probability mass function. And then we also need to compute the cumulative distribution function. So the easiest way usually to compute the cumulative distribution function is to add the successive probabilities in order. So we can see we need to split up the real line into 5 intervals. So we have 3 intervals in the middle between the relevant values, and then we have a left infinite interval where t is less than -3, and we have a right infinite interval where t is greater than or equal to 8. And so we can say, okay, so if t is less than -3, there's no zero probability the random variable is less than -3 because all the values are bigger than -3. And then we can say, all right, so to get the next interval, I'm going to add 1/7 to 0. Then to get the next interval, I'm going to add 1/3 to 1/7. To get the next one, I'm going to add 5/14 to 10/21. And then I can either add 1/6 to 5/6, or I can just cheat and say the right infinite interval is always 1. So, yeah, that's how you can compute the cumulative distribution function directly from the probability mass function. And as you can see in the solutions here, I'm not really insisting on any kind of explanation beyond just providing the requested data. Okay, so now we have this problem 6, where it says, let A and B be independent events in a probability space which are each less than certain. Determine the value of the following quantity. So if I were looking at this question, I would be like, wow, there isn't much information here. It's like, it says A and B are independent events, okay, and then it says they're less than certain, but saying they're less than certain is obviously just because the question writer is paranoid about dividing by 0, and they don't want P of A to be 1 in the fraction, which would make us divide by 0. So if we ignore the question writer's paranoia about division by 0, then we can see all we really have here is that A and B are independent events in a probability space. So we're asked to determine the value of this weird-looking expression. And you can think pedagogically for a moment rather than mathematically and think, well, look, if the question writer is telling me I'm supposed to determine the value of this quantity, and they're not giving me any indication that it should, about what form it should take, I can clue in from that there's probably some sort of magical simplification where this quantity actually is less complicated than it appears to be, and it always comes out to be the same thing, because the question asks me to determine the value of something which is superficially a variable. But when you're asked to determine the value of something which is superficially a variable, in a pedagogical context, you can say, okay, I should expect some magical simplification where all the variables disappear and this comes out to be a single numerical quantity no matter what A and B are. So if you want to figure out what the right answer is, you can just say, all right, let me pick any two events I want. For example, I can say that the probability of A and B are both 0. If you have two impossible events, it's easy to check that so let's say A and B are both impossible. Then I can say probability of A and B is 0. Probability of A times probability of B is 0. So two impossible events are always independent of each other. And if I plug in zeros for all the probabilities, I get 1. So I know that the answer to the question is supposed to be 1. I just need to figure out why. And so once I know that the answer to the question is supposed to be 1, I can start thinking, well, okay, what I need to be doing here is to try and massage the numerator somehow to end up being the same as the denominator. And so with that goal, let's see what we can do. So I've said here that in the solution to problem 2 on the practice midterm, the following equation was derived. So first of all, let's try to think why this equation is helpful in the question. It's helpful in the question because independence tells us something about the probability of a conjunction. And so if I use this equation to turn my A or B into something involving A and B, then I have some hope to exploit my hypothesis of independence, which is literally the only hypothesis the question gives me other than paranoia about division by 0. So it's like I only have one hypothesis, which tells me I can turn conjunctions into products because of independence. So if I only have one hypothesis, I need a conjunction to appear somehow so I can turn it into a product with the definition of independence. And so the equation I have here, which I've cited from the solution to problem 2 on the practice midterm, is exactly suited to turning disjunctions into conjunctions. So, there's a lot of equations that have appeared in the lecture notes and the practice solutions, and I can't necessarily give you a super clear idea of how you're supposed to realize that this equation is the relevant one. What I would have done to try and think about this myself if I were solving the problem is I would try to just browse through all the lecture notes and solutions and look for equations relating disjunctions to conjunctions. And this equation you see that I have cited here is really the only one we've come across in the course which explicitly relates a conjunction to a disjunction. So how I would, go about finding this equation from all the other equations that we've seen in the course is I would say, well, look, I know I'm supposed to be turning a disjunction into a conjunction somehow, and therefore, I'm just going to kind of visually search for equations which relate disjunctions to conjunctions. And if you do that search, looking for equations relating disjunctions to conjunctions, you'll find that this equation I have here is really the only one that does that in a substantial way. So now that I have this equation, I can rewrite the numerator of the fraction as 1 minus the probability of A minus the probability of B plus the probability of A and B. And so this is good, or at least it looks good because now I have a conjunction. And because I have a conjunction, I have some hope to apply my hypothesis about independence. Okay, so we can just multiply out the denominator of the fraction, and then we can do what we need to do, which is involve the definition of independence somehow. So when we expand the denominator, we get this probability of A times probability of B. And now we're like, yes, good. I have conjunction and I have product. And these things are exactly what's supposed to be related by the definition of independence. So when I substitute in the probability of A conjunction B for the probability of A times the probability of B, I can see that I have this expression 2 for the numerator, I have the expression 3 for the denominator, and the two expressions are identical, so the value of the fraction is 1. Okay, so I'll end the lecture there. Hopefully I should be able to fix my internet access issues, and the new material lecture on Wednesday will be uploaded according to the regular schedule. Okay.